Hi, everyone. We're just going to give it a minute to let people continue to join, and then we'll get started. Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar on nutrient removal optimization for small wastewater treatment plants. My name is Owen Volk from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics, and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box at any time throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and any other information you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have any questions or need assistance, please contact smallsystems@syr.edu. Now, for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. One of the many ways that the EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application, falling short on project funding, not sure where to start? EFCN is here to help. Submit a request through the link in the chat to receive tailored support based on your project needs. And on that note, we can get started. I would like to introduce our presenter for today, Gregory Pearson, Water and Wastewater Trainer at the Great Lakes Environmental Infrastructure Center. Welcome, Greg. I will go ahead and hand it over to you.
Thank you, Owen, and welcome everyone. And is my video and audio coming through good, Owen?
Yep, audio sounds good and we can see your slides.
Okay, wonderful. As Owen mentioned, today we're going to be talking about nutrient removal optimization. And I want to kind of define the problem statement. A lot of us have wastewater treatment plants that were designed mainly to remove BOD, TSS, and oxidized ammonia. They weren't primarily designed to remove nutrients. So how can we optimize these types of plants to remove nitrogen and phosphorus? And today, I'm hoping that we can accomplish three main objectives here. To understand the underlying processes for nitrogen and phosphorus removal using organic removal processes. Understand how we can apply some modifications to wastewater treatment plants to improve nutrient removal, and finally have some way to analyze process monitoring control results. We're going to start with a little bit of review because we'll look at the activated sludge process, which kind of exemplifies the secondary treatment process in wastewater. We're using biological um, microorganisms to consume waste. If we look at a layout, a basic layout of a plant, we have our preliminary treatment where we're screening out large materials, and we usually have settling in a primary clarifier where the solids that are ready to settle out without any treatment can settle out. And we'll be using this term primary effluent, means the effluent that's coming out of a primary clarifier. That's also the influent to the activated sludge process. And when we get to the aeration tank and the secondary clarifier, that's our secondary process, or our activated sludge process in the wastewater treatment train. And it's important to notice that what's entering from the primary clarifier effluent is those solids that would not settle by themselves without treatment. So it's non-settleable suspended solids, and there's also some dissolved solids. And so what happens in this process is waste in the form of BOD is converted to microorganisms. It's cellular biomass of organisms that consume the waste and grow and reproduce, and that's settled out as sludge. If we zoom in on just the activated sludge process here, you see it consists basically of an aeration tank and a secondary clarifier. We have our primary effluent coming in, and then the sludge is settled in the secondary clarifier, which consists of a large amount of microorganisms. And these microorganisms are circulated back to the influent, and together the incoming waste with the return activated sludge creates what we call a mixed liquor. So we have mixed liquor suspended solids, which is a combination of the activated sludge microorganisms that were settled out in the clarifier and the incoming waste. So you have the eaters and the food coming together in that aeration tank. And this is an image here of an actual aeration tank where you see the return sludge and the primary effluent coming in at one end of that tank. By the time we get to the other end of the tank, the food has been consumed. There's two basic process control equations that we use in the activated sludge process, and we're going to connect this back to nutrient removal in a moment here, but we're just reviewing right now. The first is the food to microorganism ratio. So we're basically, we can't control the amount of wastewater that's coming in, so the food kind of remains constant, but we can control the amount of microorganisms that we recirculate back to the aeration tank. And so if we have more bugs, more sludge that we're circulating back to the aeration tank, the FM ratio will become smaller. And if we have less, it will become larger. Basically, for nutrient removal, especially for nitrogen removal, we want to have a lower FM ratio, which means we're going to be holding more microorganisms than we would just for removing BOD. The MCRT is the mean cell residence time, and the word mean means average in this case. The average time in days that the microorganisms remain in the system. We're recirculating the solids where they settle out in the clarifier. We're recycling a large portion of that back to the aeration tank, and it settles again, and we recirculate it back again. And so it will remain in the system for a number of days. The MCRT for activated sludge, for conventional activated sludge, can range anywhere from 5 to 15 days. For nutrient removal, we're holding that sludge a little bit longer. We're recirculating it a little bit longer than we would just for BOD. So we're going to be closer to the larger part of that range, and a lot of experts recommend at least 10 days for nitrification. For extended aeration, something like an oxidation ditch, we have a longer time that we retain sludge at 20 to 30 days. And here's the equation that we use for that. We look at the total amount of pounds of solids that we have in the activated sludge system. We have some the recirculation of the sludge into the aeration, and we're holding a certain concentration of mixed liquor suspended solids. And then we divide that by the pounds per day of solids that are leaving the system. So we have a waste sludge flow as well. So if we turn the waste sludge flow higher, it'll shorten that MCRT. And if we lower the waste sludge rate, it'll increase the MCRT. The FM ratio ranges from about 0.25 to 0.45 for conventional activated sludge. So for every pound of microorganisms, there's a quarter pound of BOD to consume. So there's more microorganisms than food. For extended aeration, it's a lot lower, from 0.05. 0.05 is 1/20th. So for every 20 pounds of microorganisms, there's 1 pound of BOD. So the FM ratio is calculated by looking at the pounds per day of BOD waste that's actually entering the system from that primary effluent, and we divide that by the pounds of microorganisms that are in the aeration tank. So that's just kind of a review of that. Some other process control that we use for activated sludge in general is by examining sludge. We can examine the sludge by looking at how well it settles, and we can look at the actual sludge flocculation particles, and you can see you can have poor settling where you have either sludge that's too young or too old, and when it's just right, it flocculates well and settles well. And so we're monitoring that because we want our biomass, our microorganisms, to be healthy, but we also want them to settle well. We also can do a settling test where we measure the sludge volume index, and we're looking at how much volume is required for that settled sludge out of a 1 liter sample. There's a connection between settling, how well sludge settles, because ultimately when the sludge is treated and you get rid of the waste, you also want it to settle and be something that you can handle and dewater, and you want also rapid, efficient settling. And there seems to be some sweet spots. There's conventional sludge here that range of FM ratio between 0.25 to 0.45 seems to be the best settling. And then there's a little period in between those, between conventional and extended air, where it wouldn't settle well. But when you get to extended air, there's also a sweet spot between about 0.05 to 0.15 where the sludge will settle well. And finally, we can examine microscopically and look at the kind of organisms that are in activated sludge. Bacteria and amoeboids, the more simple forms of microorganisms, are associated with a short MCRT. You're not retaining the sludge long enough for much complexity to develop. As you hold the sludge longer, you might get things like stock ciliates. And then finally, if you hold the sludge a very long time, especially in a situation like extended aeration, you start getting more complex organisms like rotifers. So you can microscopically evaluate the sludge as well. These are all process control. Now we're going to shift here from that kind of short overview or review of things that most of us probably are already familiar with, and shift to nitrogen and phosphorus, which is the 2 nutrients that we're primarily concerned with when we talk about nutrient removal. These both cause problems in receiving waters because they can lead to eutrophication. Basically what happens is you have excess nutrients that enters the water, and it results in plants growing, mainly algae. The algae grows and it blooms. It can release toxic substances, but the main problem is you have all of this plant mass that's grown now. It can block sun and so forth and clog fish gills, but eventually it dies off. And when it dies off, it causes oxygen depletion, and the oxygen will be used up, and then you can get fish kills and a lot of problems with aquatic microorganisms. You can also have, if that same drinking water source is used downstream for a drinking water source, You might have to chlorinate water more because of all the products that are in the water, and it can lead to disinfection byproducts, and it can also harbor harmful microbes. And finally, another issue that we're also dealing with is that ammonia is toxic to aquatic life. And so most of our treatment plants that aren't optimized for nutrient removal will already be oxidizing ammonia. But a lot of times we don't remove total nitrogen or total phosphorus. In general, about 85 to 90% of BOD and TS is removed in traditional conventional activated sludge plants, and between 90 to 95% of the ammonia is removed. And when I say removed, if you measured the amount of ammonia in the effluent, you would say, well, it's either non-existent or it's very low. But really, it's only been oxidized to a different form of nitrogen, so there's still nitrogen present. So if we have a permit limit that we need to meet for nitrogen, we might have to modify our plant so that we can not only nitrify but denitrify. And phosphorus is also a difficult nutrient to remove. Some removal does occur naturally because microorganisms need some nutrients to grow. So some phosphorus is removed as part of the activated sludge process or any treatment process. Some phosphorus will be removed and settled out hopefully as sludge, but usually not enough to get down to the very low levels of phosphorus when you're looking at permit levels. In some cases, 0.1 milligram per liter, and you might have 7 or 8 milligrams per liter of phosphorus. We're going to go to our first poll now, and this is kind of our review section. Which of the following describes how conventional activated sludge treats wastewater? What's the big concept of activated sludge? And Owen, as you probably already know, I'm not going to be able to see the poll, so you go ahead and feel free to let us know what the percentages are.
Absolutely. Got it launched. I'll just give it a little bit and I will get you updated. Okay, gotta give it another about 10 seconds. Okay, so the results of the poll, 3% said that solids are filtered out through a semi-permeable membrane. 76% said a population of microorganisms is retained to consume wastes. No one said solids are vaporized through high oxidation levels, and 21% said all of the above.
Okay, well, very good. The majority in this case had a population of microorganisms is retained to consume waste, and that's correct. We're collecting those microorganisms in the secondary clarifier, and we're recycling them back into the aeration tank, and those microorganisms are hungry and they consume that BOD that's coming in. And of course, we're aerating too. We're creating the perfect environment for those incoming waste to be consumed quickly. The solids that settle in the secondary clarifier consist of about 70% microorganisms, and the microorganisms, they use that oxygen as they're consuming the waste. Now, we're moving into some biological nutrient removal processes. First of all, there's nitrogen removal, which consists of nitrification. And denitrification. In nitrification, we're converting the ammonia to nitrate. And then in denitrification, we're converting nitrate to nitrogen gas. And that occurs in an anoxic atmosphere, which we'll explain a little bit more of in a moment here. We'll also talk about biological phosphorus removal. And basically there's two steps for that as well. We have an anaerobic environment, which helps us to build the population and energize this population of what we call phosphate accumulating organisms, PAOs. And then we have an aerobic stage where these PAOs go out and accumulate phosphorus into their cellular bodies, and then they're settled out as sludge. And we're going to go through each one of these separately here. So nitrification, as I just mentioned, it occurs in an aerobic environment, and this is occurring in a regular unmodified activated sludge plant as well. We're converting ammonia, NH3, to nitrate. And you can see the little cycle there on the right-hand side of your screen. You start out with ammonia, NH4, and we nitrify it to NO2, which is nitrite, and then that's oxidized to nitrate, NO3, and then finally another step is denitrification from NO3 to N2, the N2 gas. And this nitrification is a two-step process here. We have nitrification, then denitrification, and you can see the transformation from ammonia to nitrate, then from a nitrate to nitrogen gas. And we can kind of go in a little bit farther and look at a little bit more details. Nitrification actually requires two different types of bacteria. We have ammonia, NH3, being oxidized to nitrate by nitrosomous bacteria, and then nitrite is oxidized to nitrate by nitrobacter bacteria. So there's actually two different microorganisms that are responsible for helping us to nitrify ammonia. And these bacteria, the nitrifying bacteria, they're very sensitive. We were talking a little bit earlier about holding a higher mass of microorganisms for a longer time. A part of that is because we want to build a population of bacteria in the activated sludge flow. Also, we want to carry a higher amount of microorganisms in the aeration tank because we want to bring in as many of these nitrifying bacteria as possible. And these bacteria are pretty sensitive. They're sensitive to pH, temperature, any kind of toxins can result in them either not being able to nitrify or even dying. Also, they're also sensitive to overpopulation of the other bacteria. The heterotrophic bacteria that are consuming BOD can basically outpopulate them. And so they're, instead of being one every 1,000, they become one every billion, and they're like a needle in a haystack. They can't effectively nitrify. So you want to take some steps to make sure you are nurturing the population of these bacteria. They also grow best when most of the BOD is gone. And so I'm going to show you a diagram of illustrating that, but most of the BOD needs to be treated before these nitrifying bacteria can really function. And one final point is when you have a plant and you have an NPDES permit, there's going to be definite limitations on ammonia. And if you oxidize all the ammonia to nitrate and you meet the limitations for ammonia and nitrate, you're done. You don't need to denitrify. But if you have a permit that requires you to get rid of some of the nitrogen, then you would have to denitrify to actually remove nitrogen from the process. The denitrification process, it requires anoxic conditions. Anoxic means it contains nitrate, but no dissolved oxygen. So the bacteria are going to use that nitrate as their oxygen source. And this bacteria that is responsible is called Pseudomonas bacteria. And they prefer to breathe oxygen, but they do have the ability to extract oxygen from nitrate. And they need a food source or some kind of carbon source. So as they're consuming something like BOD, they also need oxygen to process that food. And so they will strip oxygen from nitrate using special enzymes. Those two volts are what I just said. And they do require a carbon source. And so in the treatment train, near the end of the oxidation tank or the aeration tank, if you think about it, you get to the end of the aeration tank and the BOD is gone and you have nitrate. So you basically have a situation where you have nitrate, but there's no BOD to consume. So that creates a little problem for us. And that's what we're gonna talk through next. Now to nurture the nitrifying bacteria, here's a couple tips that we need to know. First of all, we need to have a plant that is removing at least 80% of the BOD. Our dissolved oxygen needs to be above 2 milligrams per liter. They're also sensitive to temperature. The optimal range is between 77 and 86 degrees Fahrenheit, or between about 25 and 30 degrees Celsius. And if you look at different research reports and different studies and manuals, these temperature ranges vary quite a bit. But in this general range is where nitrification proceeds the fastest. As you drop in temperature, about every 10 degrees Celsius in temperature, or about every 18 degrees drop in Fahrenheit, the nitrification rate decreases by about 50%. Also, we need to know that we have enough alkalinity. You notice NH3 has an H in it, and hydrogen, and nitrate is NO3. So where did that hydrogen go? Well, some of it goes into water, but there's a lot of positive hydrogen ions also floating around that are acidic, and they can create a drop in pH, and that a drop in pH can stop nitrification. So we want to make sure there's plenty of alkalinity, and ideally we want the pH to be around neutral and up to 7.5. If we get down too acidic, like say we drop down to a 6.5 pH, that can seriously decrease the nitrification rate. And we want to hold our solids for a little longer, near the higher end of our plant. And a lot of sources recommend at least a 10-day MCRT. So basically a little bit lower FM ratio and a higher MLVSS than you would if you were just trying to remove BOD. And so here's a little diagram here. You see the ammonia on the left-hand side of the screen, and you'll see ammonia as NH3 or NH4. The NH4 is the ionized version, the ionic version of ammonia, but it works the same with both. But as you oxidize ammonia to nitrate, you see there's an H plus atom that comes off of that. And if you follow the H's from the NH3, I highlighted the H in red, over to the right-hand side of the equation, you see you have well, at least one of those three forms a water molecule, and there's two floating around to cause a decrease in pH. And in general, about for every 1 milligram per liter of ammonia, you want 7.14 milligrams per liter of alkalinity. And if we look at the effect of pH on nitrification rate here, we see here, if we look at 7.5, a pH of 7.5, that we're about at a 70% of the max nitrification rate. And if we look at 6.5, we're down to around 25% of the max nitrification rate. So it affects pH, but the pH affects the nitrification rate quite a bit. And keep in mind, this particular diagram is not for all temperatures. This is just for a particular temperature here, but the concept is the same. If you have a decrease in pH, it will decrease alkalinity. I'm going to give you an example here. We have a wastewater plant that has alkalinity of 150 milligrams per liter as calcium carbonate, and it has 15 milligrams per liter of ammonia. And we're going to ask how much alkalinity would be used up by complete nitrification of the ammonia, and how much alkalinity will be left over, will remain in the wastewater. So if we want to know how much is going to be used up, we can take that 15 milligrams per liter of ammonia and multiply it by 7.14 parts of alkalinity for every one part of ammonia, and we get 107.1 milligrams per liter of alkalinity that's required for the nitrification. And if we want to know how much is going to be left over, we take the incoming, the amount that we started with, 150 milligrams per liter of alkalinity, minus the 107 milligrams per liter of alkalinity that was used up, and we have 43 milligrams per liter of alkalinity remaining. And in general, we want to have a minimum of about 50 milligrams per liter of alkalinity remaining after nitrification so that we can protect from pH drops. And some sources say that they want to shoot for 75 milligrams per liter of alkalinity. So if you have a problem where you have low alkalinity and the nitrification is going to use it up, you can help yourself out by adding some alkalinity. And usually that would be something like sodium carbonate or lime to increase it. Now I want to give you a little diagram here. We have our aeration tank, and in that aeration tank, we're wanting to have adequate temperature. If we're in a cold country, we might want to have some kind of a structure that or cover to help keep the temperature up, or maybe even some, we use our biogas to kind of heat the room that we're doing this aeration in. Sufficient alkalinity that we just covered, the pH 6.8 or over ideally. We want to have plenty of DO, at least 2 milligrams per liter. 3 is better. Sufficient amount of solids, microorganisms in the tank, and we want to have no toxins. So those are all the conditions that we want to have in that tank. And we want to remove at least 80% of the BOD, and theoretically that should happen before we get to the end of the tank, and then nitrification is able to occur more efficiently once that BOD is removed. The flow is moving from the left to right through this tank. And at the end of the tank here, we have low BOD and low ammonia, and we have basically a lot of nitrate in the water at this point. No BOD, no ammonia, just nitrate here. And also another thing is we don't want to allow our microorganisms to hang around in the clarifier too long. These nitrifying organisms, they could start to die off after about 4 hours. And so we want to maintain a good population of microorganisms so we can make sure we have enough nitrifying bacteria. So we have our effluent going out. There's no ammonia there, but what about nitrogen? We still have nitrogen, so we need to figure out a way to remove nitrogen by denitrifying it. And so let me just stick an anoxic tank at the end here. And so if I did that, an anoxic tank where we have there's no aeration, no DO, and we already have nitrate in the water, creating an anoxic zone. What would be the problem of putting it there? Well, at that point, there's actually no BOD present. So the bacteria don't have anything to eat. So there's no reason for them to use the nitrate. Also, if we were to have denitrification occurring in the clarifier, we could actually have problems with rising sludge, and the more we keep the oxygen off from all those microorganisms in the clarifier, we could start to get some sick microbes. We want to keep those microbes as healthy as possible so that we can recirculate them and they're hungry and ready to consume. Now, the normal solution for biological treatment nitrification and denitrification is to put the anoxic tank in this position and to have a nitrate recycle flow. And so right here at the end of our aeration tank, we have nitrates, but there's no BOD, and we recycle that flow back to the anoxic tank. And those nitrates will be available for the incoming BOD and the microorganisms to consume the BOD using nitrate as their oxygen source. So you have your denitrifying bacteria, which can thrive in an anoxic environment, and that BOD is coming in, and the nitrate is being stripped of its oxygen. And now in this case, here we have the denitrifying bacteria actually have a food source to consume and a source of oxygen in the nitrate. And that nitrate is converted to nitrogen gas, which is going to bubble off into the atmosphere. Now here's another way that denitrification can occur. We have a final tank after the clarifier that is an anoxic tank, and sometimes they might use a denitrification filter. In both cases, the effect is the same. They add an additional carbon source, and a most common one is methanol, and that is what the denitrifying microorganisms will consume instead of the BOD. So they'll be eating the carbon source, and as they eat, they require some kind of oxygen to process that BOD, and so they'll strip the oxygen from nitrate. And this particular solution, you don't need to recycle the flow back to the beginning of the aeration basin or even use BOD. So they use an external carbon source, and there's lots of different sources that have been experimented with and used. Methanol is the most common one. And so optimizing these bacteria, you want to maintain a high MCRT, a lower FM ratio, control the pH of the system, maintain a high DO, and prevent toxins from entering the system. That's just a little reiteration of some of those concepts. Denitrification is much less sensitive. It can proceed across a pretty wide range of temperatures, from 5 degrees Celsius to 60 degrees Celsius, and across a pretty wide pH range from 6 to 8. So they're less sensitive. However, we do need to know that there's enough carbon present for them to consume. It also has an added benefit of adding back in some of the alkalinity that was taken from the nitrification process, because the conversion to nitrogen gas releases some hydroxide ions. And we're going to go to poll 2 now, and we're asking you to do a little bit of math. I hope you have a calculator handy or one on your phone, because we have a problem here. The influent wastewater has 195 milligrams per liter of alkalinity, and we have an incoming concentration of ammonia of 20 milligrams per liter. So we want to estimate how much alkalinity is left over after complete nitrification. And just to give you a little reminder, every milligram per liter of ammonia requires about 7.14 milligram per liter of alkalinity.
Okay, the poll is running.
Have I put you all to sleep out there? Send me a message in the chat if you're able to, if you're following along, if I'm having the right pace and if I'm explaining the concepts clearly enough.
I'll let you know what people say as they roll that in through the questions tab.
Yeah, and
We
as
got
you
one
have
person
questions,
saying all good so far, and we do have some questions. I'm getting those saved up for the end.
Good.
Okay, I'm gonna give the poll just a few more minutes, just because we're Well, a few more seconds. My apologies. Okay, awesome. So we're gonna close that. I will share those with the group. So 12% said 32 milligrams per liter. 42 milligrams per liter was at 14%. 52 milligrams per liter was the majority at 72%. And 62 milligrams per liter, it was at 2%. Also, everyone is responding that they're learning a lot and things are going well.
Okay, good. Thank you everyone for the feedback. I'm going to show the solution here to calculate the alkalinity that was used up by nitrification. We take that 20 milligrams per liter of ammonia, times it by 7.14 to estimate the amount of alkalinity that we need, and we get 142.8 milligrams per liter of alkalinity that's going to be used up when we nitrify. So we subtract that from the 195 that was coming in. 195 milligrams per liter minus 142.8 gives us 52.2, and I rounded it down to 52. So great job on all of you who got that correct answer. And for those of you who chose another answer, this is the solution. Now we're going to talk a little bit about biological phosphorus remover. It's kind of a two-step process here. We first of all create an anaerobic zone. Anaerobic means there's no oxygen and there's no nitrate. There's no form of oxygen whatsoever. And we hold it in that anaerobic zone to the point where it doesn't go septic, but it's called fermentation. It's kind of between septic and aerated. These special organisms are called phosphorus accumulating organisms. And in this anaerobic zone, they basically have a chance. They don't have any competing bugs. Aerobic organisms can't live in their anaerobic zone. The facultative organisms that could breathe nitrate, they can't live in this zone. So it gives them a chance to grow and increase their population and to kind of become energized. They consume fatty acids and nutrients in this zone, and they become energized and populous. And then when we go to the aerobic zone, they are ready to take phosphorus into their bodies. They're actually able to accumulate phosphorus into their cellular mass, and then they're settled out as sludge, and that's how the phosphorus is eventually removed. Now, given those, we have that's all we're going to say about the phosphorus right now. And we're going to look at some examples of how nutrient removal can be done in some different formats here. Here's an oxidation ditch, which is a form of extended aeration. The wastewater is aerated as it flows around this, what they call a racetrack here. You see the plant flow coming in on the left in this diagram, and it travels, in this particular one, it's traveling in a clockwise manner. You have a mechanical aerator here that is providing DO and some motion to keep the flow going around. And you can see on the bottom, there's the effluent coming out and going to the clarifier, and there's also a waste return activated sludge flow and a waste sludge flow as well. Now, one of the ways that these can be easily modified to denitrify, we already have aeration, so we're removing BOD and TSS, and we're also oxidizing ammonia to nitrate. So that we're already doing that in this. But if we wanted to denitrify, we need an anoxic zone, and we could do that by manipulating one of the aerators. We could shut it down periodically, or we could have it function on some kind of a SCADA system according to a downstream oxygen sensor, so that it runs out at a certain point. And the DO would run out, and we'd have only nitrate available, and create, in that way, create an anoxic zone right in the oxidation ditch. And so that's one way to have nitrification and denitrification in the oxidation ditch. And sometimes they can use kind of a special chamber at the end of a oxidation ditch and create an anoxic zone where the influent is coming in through that anoxic zone. And then when it enters the aerobic zone, it's removing BOD and oxidizing ammonia to nitrate, and then basically it's recycling. It's going back in to that zone. It's the dissolved oxygen is gone by then if we've designed it correctly, and it's going back into the anoxic zone. Just like that activated sludge example, we have a recycle flow. A oxidation ditch is designed for phosphorus removal only. We could create an anaerobic zone where there's no oxygen and no nitrate, so we're not going to have any recycle in this case because we wouldn't want to recycle nitrates back into there. So it's anaerobic to prepare the phosphorus accumulating organisms, and then they're prepared once they enter the aerobic zone. Those phosphorus accumulating organisms are uptaking phosphorus, and also the other things that are going on in that aeration zone is BOD removal and ammonia oxidation. Here's one that's designed for both phosphorus and nitrogen removal. We have an anaerobic zone where there's no oxygen, no aeration, no nitrates, and that's preparing those phosphorus accumulating organisms. And we also have an anoxic zone, and we're going to have some recirculation flow back to that. So that's for denitrifying the bacteria. It's not the first step. We create the nitrate first, but the way the flow occurs, we flow through that zone into the aerobic zone where we remove BOD, oxidize ammonia to nitrate, and uptake the phosphorus. And then we flow back into that anoxic zone, and that nitrate is converted to nitrogen gas. And the phosphorus is settled out as sludge eventually. Now here's a activated sludge plant that was designed to have all three of those environments. We have an anaerobic zone, an anoxic zone, and then our aeration zone here. So in the anaerobic zone, we're preparing our phosphorus accumulating organisms. The anoxic zone is denitrification, and in the aerobic zone, oxygen-rich atmosphere, we have the BOD is being removed and ammonia is being oxidized. And notice at the bottom here, we have our nitrate recycling flow. It's bringing that nitrate-rich flow back to the anoxic zone, where the denitrifying bacteria can use nitrate to consume BOD, because BOD is flowing through from the left through the plant to the right. And nitrogen gas from that anoxic zone is bubbling into the atmosphere. And the phosphorus is removed in the sludge. There's another form here where they have it's kind of a AO, they might call it. You have an anoxic tank followed by an aerobic tank. First of all, hopefully you can see my pointer in this area here, you have that nitrified recycle, that same process we've been kind of talking about. But we also, we have a second anoxic tank where you could either repeat the process, but more than likely you could add methanol there, or a form of carbon, so you wouldn't be recycling that. So that could be like a polishing tank. And then a final aerobic tank to make sure you have nice healthy organisms in the clarifier. Some operators have taken the initiative and different places around the United States, and they've experimented with their treatment plants to make them function for nutrient removal. And one operator here in Montana, he began just turning off one of the aerators for 1 hour at a time and then 2 hours at a time to create an anoxic zone to facilitate denitrification for nitrogen removal. And you can see right now here on the bottom of this image, you can see one of the aerators is on, and the one on the top of that image is obviously off. You can see that it's not creating any turbulence there. So he's doing that to facilitate some nitrogen removal. And just by doing that, was able to reduce nitrogen in the effluent from 25 down to about 5. It was pretty labor intensive, but he was able to do it. And here's an example of the actual results here. And you can see this was over a long period of time, but between about 2013 and 2014, you can see there was a lot of, or between 2012 and 2014, there was a lot of experimentation to keep perfecting this technique. And we're going to go to poll 3 here. And this question asks, what condition is necessary for denitrification to occur and why? And the point of this question is, if we wanted to experiment with our plant and we wanted to remove nitrogen and we wanted to have denitrification occurring, we'd have to think about what kind of a tank or what kind of a tank environment do we need and where should it be located in the treatment train. And knowing how the process works and what kind of environment we want to create would help us to do that.
Okay, so we have the poll running. Let it go probably another half minute. I will say there's a lot of very good questions coming in.
Okay.
With the amount that we have, there's a solid chance we won't be able to get through all of them in the session. So just to let everyone know, I will send them to Greg and include them in the follow-up email that is sent out.
Yeah, I like doing that too, because I can put a little more thought into some of the more complex questions. But I'll try to answer as many as I can today, if we can get there.
I have faith that we will. Okay, so we're gonna close this out and get the responses to you. So 79% said anoxic to force bacteria to consume oxygen from nitrate. 6% said anaerobic to change the ORP of wastewater. 4% said septic to cause bacteria to consume nitrogen, and 11% said aerobic to ensure that nitrogen gas is oxidized.
Okay, let's take a look at the answer here. And the anoxic environment means that the only source of oxygen is nitrate. And if we have nitrifying bacteria and we have something for them to eat and we have nitrate there as their only oxygen source, they'll be forced to use it as food, and they do that by stripping the oxygen from nitrate. Another operator went another path where it wasn't quite so labor intensive. An operator in Great Bend, Kansas, modified their oxidation ditch to remove both nitrogen and phosphorus. So they created an aerobic zone for the phosphorus accumulating organisms to grow and be prepared to accumulate. And the interesting thing they did, they put an oxygen probe downstream to monitor the oxygen level. They're trying to adjust the oxygen, their aeration, so that the oxygen would run out at a certain point and create a permanent anoxic zone. So they had their surface aerator was controlled with a VFD, a variable frequency drive, that would allow that motor to run at any RPM that was necessary. And it ran according, through a SCADA system, according to what the DO probe. So if the DO probe, if they wanted it to go from, 2 milligrams per liter oxygen down to 1 and then down to 0, maybe they were monitoring a little bit upstream of that. And if the DO probe said, hey, we got 1 milligram per liter, then it would slow down. If it said, hey, we got only 0.1 here, maybe it would come on a little bit, but they controlled it with a SCADA, and it took them a while to get it fine-tuned, but once they did, it worked. And they had a project that was going to cost them about $6 million, and they were able to save. They didn't have to spend that money because they figured out a way to make this oxidation ditch remove both nitrogen and phosphorus and meet their permit. And here's an example of that permit there, and you can see that in the bottom image there, you can see there's some aeration going on in a portion of the ditch, and the aeration looks to be off in a portion of the ditch. They created an anaerobic zone where the waste would come in, and then they had an aerated aerobic zone, and the aeration was set to run out of DO at a certain point to create an anoxic zone for denitrification to occur. And in that anoxic zone, the only source of oxygen was nitrate. And so the process environments that we've been talking about here, aerobic, we're looking at 2 to 3 milligrams per liter of oxygen, and we're consuming BOD and oxidizing ammonia and allowing uptake of phosphorus by the phosphorus accumulating organisms. In the anoxic environment, we have only nitrate as a source of oxygen. There's no DO, and that allows denitrifying organisms to strip oxygen from the nitrate. It requires some kind of form of carbon, BOD, methanol. And in anaerobic, there's no source of oxygen of any kind that allows those PAOs to grow and become energized. Now this requires some BOD and nutrients. So that's why a lot of times or all the time I should say, you see these at the influent where the wastewater, the unaerated wastewater is flowing in. One way to monitor this process is having an ORP probe. An ORP probe is oxidation reduction potential measurements. And so a positive ORP means you have oxidation going on, and a negative value is a reducing environment, like an anaerobic environment. So the anaerobic environment that we're looking to produce, our ORP reading should be around negative 200 millivolts. The aerobic, on the other hand, it's oxygen-rich oxidizing environment, around a positive 150 millivolts. And the anoxic environment for denitrification around negative 100 millivolts. And once we attain these environments, we want to hold them there for a while, at least 30 minutes, so that that these functions that are listed here can take place. And a lot of times we'll see that recycle flow back from anoxic back to the aerobic because we're trying to bring BOD in contact with the nitrates. In this particular oxygen probe here, it shows positive 217, means we have an oxygen-rich aerated environment in that particular aeration tank. Sequencing batch reactors can also be modified. They have different stages in the same tank. So if we wanted to modify that, if we wanted to create an aerobic zone, we might want to create it by having an extended period of air off during the fill cycle. That would simulate the wastewater coming in that's not aerated. And then the anoxic zone, we could probably simulate that by having an extended period of air off in the settle zone. So number 2, we react, and then in settle, if we had an extended air off period, we could run out of oxygen, and the only thing that would be left was the nitrate that we created in the react zone. There's an operator that actually did this. He had a SBR, and he started cycling between air off and air on, and he could actually see the denitrification occurring as the nitrogen gas was bubbling out. It took him about a week to create a population of nitrifiers. He started off with an hour off, an hour on, and he expanded that air off time gradually, cautiously, to 1.5, and then he went as long as 2 hours, and shortened the aeration time a little bit, so that, because you have to make sure you process enough flow for the day. And some of the process controls that he used was a timer. He measured ammonia, measured DO levels, and ORP, and the total nitrogen in the effluent went from 25 milligrams per liter down to 8. And a lot of times what you'll see is not biological phosphorus remover, but a tertiary treatment add-on where you're using chemical precipitation to remove phosphorus. And basically they're using chemicals to oxidize phosphorus and to cause it to settle. And then they just remove it through settling and filtration. I've included a link here so you can look at a case study that where they had to meet a very stringent phosphorus level of 0.1 milligram per liter. And there was 4 different utilities that used 4 different types of chemical phosphorus treatment that you can look through and learn. There's also some advanced wastewater treatment technology out there where they're actually recovering ammonia, nitrogen, and phosphate and reusing it for other purposes like fertilizers and industry, and just reducing the overall environmental impact, reusing the chemicals. And I've included a couple of links in your slides that you can research more about this. And finally, we have a final poll here that I'll let Owen bring up, and I'll be open for questions. And this is just asking if you want to modify your process to create an aerobic zone, anaerobic zones, excuse me, to create an anaerobic zone, which of the following would be the right process control measurements to know that you have an adequate anaerobic zone? And I'm gonna, well, I'll let you tell me what I should do, Owen.
Oh, regard, sorry. Okay, got the poll running.
And I can start fielding questions even now if you think it's appropriate, Owen.
Yeah, sure. We can do that in a sec. Let me just run this by people. I know a few people were wondering about getting the slides and getting a recording of the webinar. I will mention it in the closing again, but I know some people might have to leave. The questions, slides, references, all of the applicable information will be sent out in the follow-up email, which I should be doing early next week. So you will all be able to do that. If you want an access to the slides now, they also can be accessed through the handouts tab. Yeah, I guess we can start running through a couple questions while this poll is finishing up. I'll throw you one of them. Someone was wondering, does ammonia conversion happen at the same time as BOD removal, or does BOD removal have to be reduced to a certain level before nitrification?
Yeah, it's occurring concurrently, but there's so few nitrifiers compared to the heterotrophic bacteria that are consuming BOD. So there's a feeding frenzy going on near the front of the oxidation ditch, and the amount of nitrification that's the amount of ammonia oxidation that's occurring is a lot smaller until we get to the end where the BOD is removed. So there's not a clear distinction. It's just it can't really begin working efficiently until near the end.
Okay, fantastic. So let's go through the results of the poll. So 70% said DO of 3.0 milligrams per liter and ORP of plus 250 megavolts. 15% said DO of 1.0 milligrams per liter and high NO3 levels. 71% said DO of 0 and ORP of negative 200 megavolts. And 7%, sorry, said DO of 2.0 milligrams per liter and ORP of 0.
Yeah, the AN part of anaerobic means there's no DO, there's no dissolved oxygen, there's no form of oxygen whatsoever, and the ORP measurement would be negative 200 millivolts. Any other questions that I can field? Just thanks for hanging out around, everyone. I know we're a little bit over.
Yeah, let me just say, if people need to go, like I said, there will be a recording sent in the follow-up email, so feel free to go about your day. Yeah, let's try to get through at least a couple of these. Another one that I had was, is it true that denitrification adds alkalinity? If so, denitrification might be beneficial, even if not required to prevent adding alkalinity for nitrification. I think they just kind of were curious on that.
Yeah, it definitely adds alkalinity back. The problem that where we might need to add alkalinity is because the first step, the nitrification, can stop if the pH gets too low. So that's why we might need to add lime or some kind of alkalinity up front. But it's definitely a benefit that it adds alkalinity back in before it goes into the receiving water.
Fantastic. Next question was, if you add methanol, are you making more sludge to process?
Um, hmm, maybe. Um, I'm not sure. I'll research that. Could you include that question in what you send me, Owen, and I'll do some extra research on that.
Absolutely. Absolutely, I'll leave that in. Next person was wondering about the need for at least 2 milligrams per liter of oxygen throughout the nitrification tank. Uh, would that lead to high dissolved oxygen being recycled back into the anoxic section?
Yeah, well, yeah, you have to. If it if it did, you'd have to adjust the process a little bit. Yeah, you want the oxygen to match the oxygen demand, and so if you had for some reason you had like a high I flows and you had a diluted wastewater stream, and it's possible you could have more oxygen than you needed for the bugs, and you'd end up recycling some oxygen back to the anoxic tank. You're trying to avoid that. What usually happens is that the BOD being consumed by the microorganisms uses the oxygen up by the time you get to the end of the tank. And so we're hoping to have that perfect outcome. I mean, that would be ideal where all the BOD is consumed, all the ammonia is oxidized, and you just run out of DO right at that point. So that's kind of what we're shooting for. It's a timing issue.
Okay, fantastic. I'm gonna do 2 more, and then there's like 10 or 12 more that I will send you. So someone was wondering about an NBR plant and was wondering about this process through that and if there was any suggestions on that.
That's one of the big solutions that people do use. Um, the population of microorganisms on a membrane in an NBR plant is a lot more resilient, and that that can help prevent a lot of the problems of losing nitrification efficiency. So that's a good point that you're bringing up, and there's a lot of good reasons for nitrogen removal to use an MBR.
Okay, fantastic. And then the final question is, someone was wondering that for if they just wanted to clarify for the anaerobic zone for phosphorus removal, you don't want nitrates going into that zone,
Correct.
and
Yeah.
the reasoning of that.
Well, you don't want you want to have the phosphate accumulating organisms be the ones that are thriving and multiplying. If you had nitrate in there, uh, then you wouldn't have the same outcome. In this fermentation stage, you're having things like fatty acids being developed, which these phosphate accumulating organisms will consume. Um, if you had nitrate in there, they would likely overpopulate, and they wouldn't allow that breathing room that these phosphate accumulating organisms, because they're the only ones that can survive in that atmosphere at this point. And you want to get their population up as high as you can and give them the conditions they need to be healthy, so that when they enter that aerobic zone, they're ready to uptake phosphorus.
Okay, awesome. Just to reiterate again, any of the questions that haven't been answered, there are a bunch. I will send those over to Greg, get those responded, and include them in our follow-up email. But
Those
on
are
that
such
note,
good
go
questions.
ahead.
Thank you, Owen.
Yeah, of course, of course. On that note, we'll wrap up for today. Huge thank you to Greg for sharing his expertise with us. Following this webinar, you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following the webinar so that you could let us know your thoughts on today's session, as it helps us plan for future webinars on topics that are important to you and gives us pretty good feedback. Thank you again, and we hope to see you at future EFCN events.
Thank you, everyone.